Hey guys, we are considering, or I am narrating the story of a DFT, and in this story so far, we have considered the birth of the wave function and how initially it was rather physically of not much significance. There were no physical meaning attributed to it, and then Born came along and said we can consider the conjugate of the wave function, multiply it together, and come up with the probability density function. And also we saw in our previous lecture that when we play around with the wave function, the time independent wave function, one form of it, we arrive at this wonderful wave equation here. What this wave equation tells us, depending on the Hamiltonian that we are considering, we will be able to arrive at a different wave function, so wave function with different meaning and the corresponding energy associated with the wave function. Wonderful expression. Now again, we are able to do so because this is in the form of eigenvalue equation. Now when we consider the wave function of a cloud of electrons instead of just one electron like in this case, we come up with an overall wave function that includes the coordinate systems of all the individual electrons. If I have n electrons, or if I am considering n electrons in the crowd, I have to include my wave function, have to include all the coordinate systems of the n associated electrons. And when I have to arrive at such a wave function, I have to formulate such an Hamiltonian, and that gives me a wave function, the overall wave function that includes the coordinate system of all the n electrons of the electron cloud. And that Hamiltonian essentially has three components to it. One is the kinetic energy of the electrons, summing it all up, and the potential energy based on the interaction between electron and the nuclei, summing it all up together, and finally the potential energy because of the interaction between electrons and electrons. So the summing up term here, indicates that we are not talking just about one electrons, but we are summing up all the electrons together. Now the problem with such an overall wave function is it is extremely difficult for us to handle, because 10 electrons means 10 different coordinate systems. Then we need 30 different axes. So we need to reduce it into, we need to essentially do some dimensionality reduction, and that was performed by Hartree with some approximation. So he ignored the spin, he ignored the interaction between the electrons and electrons. So he came up, or he was able to express the overall wave function into the product of individual wave functions, the product of wave functions of individual electrons. And once we were able to express the overall electrons into the product of the wave functions of individual electrons, then from this overall wave function we were able to calculate the density of the electron cloud. So once this transition was possible, the overall electron wave function to that of the wave functions of individual electrons, this transition was possible, then using Born's relation we were able to calculate the density of our electron cloud. And this is what we mean by electron density, the key term in our density functional theory. So the density functional theory, the D in the density functional theory pertains to this electron density of your electron cloud, which was possible because of all these approximations and calculations. Again, Hartree product, it ignores spin and also the interaction between electron and electron. The spin is being captured by the two here. Now this is where we stopped our previous episode. We stopped here. Now let us start from this and then see how the story of the density functional theory proceeds. So if you want, this is rather, we could say, the birth point of the density functional theory, the birth point of density functional theory. Let's see how it grows. Now when we have a cloud of electrons, the wave function of that cloud of electrons is rather unique to that electrons. Let me reiterate, or let me elaborate on that. So when I have let's say a specific configuration of the atoms, I'm arranging my atoms in the FCC framework. So if I'm arranging my atoms in the FCC way or FCC structure, it is going to generate a specific electron core as opposed to that of the HCP. And since my electron cloud as the signature of my crystal structure, the electron cloud as the signature of my electron structure, the corresponding wave function is also going to have the signature of my configuration. I have a bunch of atoms. It is possible for me to arrange them as SCP or as FCC. Depending on which configuration I'm choosing, my electron cloud, the configuration of my electron cloud is going to vary. and correspondingly the wave function of my electron cloud is correspondingly different, is going to be significantly different, again based on the configuration. Now since my density is estimated from the wave function, it means that for a given configuration I'm going to have a unique wave function. So depending, if in case of FCC I'm going to have a unique density as opposed to that of a HCP. Again, for example, if I consider FCC and HCP, depending on different configurations I have, I'm going to have a unique density function. So essentially different configuration is going to give me different electron cloud, and the different electron cloud is going to give me different wave functions. And since my wave function dictate my density is also, the electron density is also going to be different for my different configuration. But one question still remains. Even though my density is going to be unique for my given configuration, what can I say about the associated energy? How can I prove that the energy associated with a given configuration is unique to that configuration? What if I have one energy that is associated with two configuration? Again, for example, what if I had one energy that is associated with two configurations? Meaning I can then have two stable states for a given condition. I can say my atoms could arrange themselves in FCC or in HCP. It's just a matter of probability. Now of course probability is accepted within the quantum mechanics framework, but this is on the atomistic scale or in the microscopic scale. So such probabilistic configurations of atoms on the higher scale or on the larger scale is not agreed. So it means for my density to be beneficial to me, to be profitable to me, I need to have a unique energy for a unique density. I need to have a unique energy for a unique density. Meaning, if my FCC is giving me a unique density, the energy corresponding to that density should also be unique. It can be greater than HCP, it can be lower than HCP, immaterial, but it should not be same as that of HCP. Only then I'll be able to compare my FCC configuration and the HCP configuration and come up with which is the most stable one. So that is only possible. So this is the foundation of DFT. The foundation of DFT is calculating the energy of the configuration and finding out which is the most stable one through the lowest energy configuration. For that to happen, my energy should be unique for my given configuration. So I need to prove that. We have to prove that this energy is unique for my given configuration. So I should be able to express this energy using density. I will be able to do this. I will be able to use it only when this is unique for a given configuration. And this was proved by Hohenberg and Korn's theorem. So this giant step towards density functional theory was contributed by Hohenberg and Korn. This giant step is for a given density, which is unique for a given configuration, the energy associated with it is also unique. So when I have a unique configuration, not only my density, the probability density function is unique, but also the energy associated with it is unique, just associated with that configuration. If I change my configuration, my density is going to change, correspondingly my energy is going to change. So there is no two states that can have same energy, or there is no one state that can have two energies. There is no one state that can have two energies, or there is no two state that can have one energy. So what we have is one-to-one mapping between my configuration or state to that of the energy, one-to-one mapping, and that allows us to express the energy based on density. So density is useful to us primarily because I don't need n frames of reference. I don't need 3n dimensions. I just need one frame of reference. So that is the reason why we need density. Now we have reached a wonderful milestone wherein my energy can no longer be described based on 3n dimensions, but just only one, or just 3-dimensional, or one with respect to only one frame of reference using my density. So I have an energy, a function that depends on another function, and that's where we get our term functional. So we saw that density was introduced, or density was helpful in reducing the dimension. Now we have functional introduced because the functional is nothing but the energy functional, and this energy functional is unique for a given configuration, and that is going to tell me what is the stable configuration. So we have introduced already density, and this function of a function is what we refer to as functional. So ultimately we have now covered the density functional, and the combination of this is what gives us the DFT. So we arrived at density, and using density we are going to calculate the energy. Wonderful. The way it was proved by Hohenberg or Kohn that there is this one-to-one mapping between the configuration, density and the corresponding energy. This one-to-one mapping, the critical step in the DFT story, they were able to prove that by an approach called as reductio ad absurdum, meaning they first assumed that a configuration is associated with two energies and proved that this assumption is absurd. So they started off with an assumption, and they proved that this assumption is absurd, thereby proving that this assumption is not possible. So there is just one-to-one mapping between the state and the energy. So this is how they showed that for a given energy density there is going to be a specific energy associated with it. So when we have a wave function of this form, that is an overall wave function that includes all the coordinate systems of all the electrons, we arrived at such a wave function using that Hamiltonian. So we want to arrive at the wave function to calculate the density. To arrive at the wave function, we have to formulate the appropriate Hamiltonian. When we were considering the overall wave function, which includes all the electrons associated with the electron cloud along with its coordinate system, we came up with an Hamiltonian, and that Hamiltonian gave us the wave function. But now we are interested in wave function that is dependent on the density of electrons but not the individual coordinate systems of the electrons. Again, so there is a significant difference between what we initially did and what we want. What we want is a wave function that is dependent on electron density, not all the coordinate systems of the electrons. Because once I have this, I will also be able to calculate the corresponding energy, using which I can say which one is the stable configuration. So I need a wave function that is dependent on electron density. So ultimately, after this question is solved, after this critical question is solved, meaning is an energy associated with a given density, or there can be two or more energies associated with it. After that question is solved, meaning there is only one energy associated with the density, once that is proved, the second hurdle was rather to come up with an Hamiltonian that is going to describe my wave function based on density, not on the coordinate systems of individual electrons. So that solution, or that Hamiltonian, was calculated by Kohn and Sham. So Kohn and Sham, they came up with and formulated the Hamiltonian that will give us the wave function that is described, that is based on the density but not the coordinates of the individual electrons. So let us consider the individual components of the Kohn and Sham equation. So of course, the first key difference that we observe here is there are no interactions. The first key difference between the original Hamiltonian and the Kohn and Sham Hamiltonian, which gives us the wave function for which describes the wave function using a density that involves only one coordinate system, is the key difference between this Hamiltonian and this Hamiltonian is there are no summations, meaning we are just considering single electrons in this formulation. So this is rather a single electron formulation. This Hamiltonian is a single electron formulation because there are no summations here. So once I make that assumption, so we are considering single electron. This Hamiltonian is a single electron formulation. So this term here is the kinetic energy of the single electron. This term is the potential energy that comes from the interaction between the single electron and the nuclei. Now this is where things get a bit trickier, because when I have the single electron, when I have all that I'm considering is just the single electron, we need to include a potential energy term that talks about the interaction between electrons and electrons. But in this framework of Kohn and Sham Hamiltonian, we are just considering single electron. We are just ignoring all the other electrons. So it means it's difficult for me, or it will be self-defeating for me to consider the interaction between this electron on all the rest, because this expression is just about only one electron. So what this term here means is, this term is nothing but Hartree's potential. Hartree, the guy who gave us Hartree product. So this term is referred to as the Hartree potential. So what this talks about is the interaction potential between one electron and the density of electrons. So of course, I'm just considering one electron in the entire formulation of my Hamiltonian, and in this case, I'm not considering the interaction between one electron with each of the other electrons. I'm considering the interaction between one electron and the density of the electron. Now, unfortunately, the density of the electron, the cloud of the electron, includes also this one electron. So it is rather self-consistent interaction. So I have an interaction term. It is just not the interaction between electron and the nuclei. I also have interaction term for electron, but this is rather an approximated interaction, and this approximated interaction is between an electron and the electron cloud or the electron density, and this electron density also includes rather the interacting electron, so it is called as a self-consistent interaction. And of course this is an approximation. I'm not exactly considering the interaction between different electrons, and all the approximations that we have made so far, so this is where things get extremely critical. So all the approximations that we have made so far, primarily involving electron-electron interaction, is rather captured and placed under this term here. So what we are essentially trying to do is come up with a wave function that is not dependent on individual coordinate systems of all electrons, but that is dependent on density. So we were able to come up with such an Hamiltonian, but such an Hamiltonian is a single electron Hamiltonian, meaning I cannot consider explicitly the electron interaction between electrons and electrons. So I consider the interaction between electron and the electron cloud that includes the same electron as well. So it's referred to as the self-consistent, meaning it involves it itself. So that potential is what we have included here in the place of electron-electron interaction. So because of all these approximations, there is going to be several inaccuracies that are associated with this Hamiltonian, with this formulation. So all these inaccuracies are included in this term. It's a corrective term, so to speak. So this corrective term is referred to as the exchange correlation. So whenever you find any work on DFT calculations, you would find this term, and now you know the meaning of this term. This exchange correlation essentially encapsulate all the deviations that have been brought in by the approximations. So once you have such a formulation for a given electron using Cohen-Sham equation, so that will give you corresponding wave function. So again, let me repeat, this is Cohen-Sham equation, and this is Hohenberg and Cohn theorems. So these are plural, these are not singular. So what Hohenberg and Cohn theorems allow us to understand is, for a given electron density, there is a unique energy associated with it. That is the first theorem. The second theorem of Hohenberg and Cohn is, the energy that is associated with this density is the lowest one. So there are two theorems. The first theorem states, for a given electron density that stems from the configuration, there is a unique energy associated with it, and this unique energy is the lowest energy. So these are the two different statements or two different theorems of Hohenberg and Cohn. Now in case of Cohen-Sham equation, it is equations because we are considering such a formulation for all the individual electrons, and then we are bringing them all together. So it's a single electron equation, but we are not considering just for one electron, we are considering it for all the electrons and bringing them all together to formulate the wave function. So we have now arrived at a wave function that does not include all the different coordinate systems of different electrons, but is based on the density of the electron cloud. So once we are able to formulate the wave function that is based on the density of the electron cloud, we will be able to calculate the corresponding, so based on the Hamiltonian, we will also be able to calculate the corresponding energies. So with this information, or with this formulation, now we will be able to calculate the stable energy of a given configuration. So the way the entire DFT operates is, you start off with offering a specific configuration. You start off with a specific configuration. So configuration, or the crystal structure in which your atoms are arranged, is something that you feed in, that's the input. So based on the input, there are two things that are calculated. One is the density, which is directly calculated. The initial density is directly calculated. Secondly, using the Hamiltonian, you are calculating the corresponding wave function of the configuration, and from the corresponding wave function of the configuration, you are calculating the density, the Cohen-Sham density. So you start off with an input that is of the configuration. So from the configuration, you are calculating initial electron density directly. And secondly, you are calculating for the given configuration, initial electron density is being calculated. Secondly, from the configuration, you are using the Hamiltonian to calculate the wave function and the corresponding density. And these two densities are rather cross-verified across one another. One density that comes from the initial configuration, one density that comes from Cohn-Sham equation. They are rather verified across each other, and once the optimized density is arrived, the corresponding energy is estimated. So you start off with a configuration. When you run your DFT calculation, you start off with a configuration. And that configuration, you are going to use that configuration in two ways. One is to calculate your initial density. The other is using the Cohn and Sham equations to calculate your density. And you have these two densities, one stemming from the Hamiltonian, one stemming from the direct input. You optimize these two, and from the optimized density, you calculate your corresponding energies. So this you can repeat for different configuration. You can repeat it for HCP of different. So when we say we are optimizing it, we are fixing our configuration, we are playing around with our parameters, and once we are able to identify the optimized density, you will be able to narrow down the corresponding parameters. So you fix your configuration, play around with the density, optimize the density to arrive at the stable configuration, and from the stable configuration, or you will optimize your energies to calculate or densities to calculate the stable energy, and from the stable energy you say this is going to be the lattice parameter. You start off with a configuration, identify the optimized energy density. From the energy density you calculate the energy and say this is going to be your lattice parameter. So that is how the entire implementation of the DFT works. Again, when this is how rather we introduce or we execute all the formulations that we have considered so far. But one key aspect that is missing is the exchange correlation. This term is rather we have not discussed so far. This appears or happens to be the thorn in our side. We don't have clear idea of it. Of all that we know of this term is, this term includes all the inaccuracies that are brought in by the approximation. So this term needs to account for all the inapproximation. So the way this term is formulated to account for all the inapproximation primarily stemming from electron and electron interaction is, there is one approach called as local density approximation or local spin density approximation. So what it assumes is that it brings in the interaction between electrons and electrons by assuming a uniform electron cloud. Again, we have one term that includes all the inaccuracies brought in by the approximations, and this term is for one way of formulating this term, that is exchange correlation, is by assuming that the electron, the given electron, is interacting with a uniform electron cloud, and this is referred to as the local spin density approximation. So using this approximation, you will be able to account for the inaccuracies brought in by the approximations. Now there is also another approach using which you can quantify this exchange correlation. It is generalized gradient approximation. Instead of considering a uniform electron cloud, this generalized gradient approximation considers a local gradient in the electron cloud. So the LSDA, that is local spin density approximation, assumes uniform electron cloud. GGA, it does not assume uniform electron cloud, it includes the local variations. So when you are using or when you are employing the DFT calculations in this framework rather to estimate the stable energy configurations, you will have to choose or you'll have to include the exchange correlations. Now there are two possible exchange correlations that you can include. One is LSTA, the other is GGA. So to sum it all up, what we can essentially do is we can fix a given configuration. So this configuration can be, say, FCC, and we can slightly vary the intratomic distance, calculate the corresponding energies based on the densities of the atoms. You fix your configuration, calculate the density, from that calculate the energy. You can play around with the distance between the atoms, thereby changing the density and correspondingly changing the energy. And when you plot it, you will be able to find the lowest energy and the lattice parameter that offers the lowest energy. So that is going to be your stable lattice parameter. So you arrange your materials for a given configuration. For a given configuration, you arrange your material at different distances. You calculate your energy for these different distances, plot it, and the lowest energy, the lowest intratomic distance, or rather the intratomic distance that gives you the lowest energy, is going to be the lattice parameter. Now you can extend this to other configurations as well. For instance, you can have such a plot. So in this case, what we are plotting is we are fixing our configuration, changing the interatomic distance, finding the corresponding energy and plotting it. Instead of just one configuration, you can choose two. You can choose FCC and you can choose HCP, and then change the lattice parameter, find the corresponding curves. And when you plot these two curves together, you will find not only which configuration is stable, but also which lattice parameter is stable. So essentially, DFT calculations can not only be used to find the lattice parameter, the stable lattice parameter, but also the configuration. That was our original goal. If you consider the entirety of the story, we represented our atoms, and the key features were lattice parameters and configurations. Now in this plot, we fix our configuration, play around with the lattice parameter, find the corresponding energies, we plot it, or we fit a curve through it, and the lattice parameter that gives us the minimum energy is going to be my stable lattice parameter. So one feature is decided. Now we want to know what is the stable configuration. So we are considering different configurations and we are arriving at the plots for the different configuration. The way we arrive at the different plots is we consider within a configuration different lattice parameters and fit in a curve through it. So we take FCC, change the lattice parameter, calculate the corresponding energies, fit a plot to it. We consider HCP configuration, change the lattice parameter, find the corresponding energy, fit a lattice parameter through it. So, and when we bring these two, these curves that are fitted together, we will see which structure is the stable one and which lattice parameter is the stable one. So using these calculations, you will be able to find not only the stable structure, but also the stable lattice parameters using DFT calculations. Now, this is rather how the DFT calculation is employed in the materials research, or one of the way in which predominantly in which the DFT calculations are employed in the material research. However, there is one critical aspect that we have ignored so far, that is these densities, they tend to change, these configurations, they tend to change, or they change themselves, even though in the minor level, they change themselves with respect to temperature. And this effect of temperature on the densities have not been considered so far. So all the stable configuration, the stable lattice parameter you get is essentially for 0 Kelvin. So when I take aluminium and I find that the aluminium is, or the stable configuration of aluminium is HCP, this is its lattice parameter. It's not that my calculation is wrong, it's because I'm doing it at 0 Kelvin. I don't know if you will get that, but still if it happens to be the case, then it's because I'm doing it at 0 Kelvin. So even though the DFT calculation promises to be something huge, it has a one big caveat associated with it, that is, it is operational only at 0 Kelvin. So what we will consider in the next lecture, possibly the last one on DFT calculations, is that we will see if there is any possible way for us to counteract this limitation, to remove this limitation, because as far as we are interested, the change in the structure, which we refer to as phase transformation, happens at considerably higher temperatures than absolute zero. So DFT calculations are not that useful for us, particularly in materials research when it is restricted to 0 Kelvin. So in our next lecture or next session, we will see how we can get rid of this limitation. See you then, guys.